Lots of people have become used to tapping, swiping, and scrolling to access information and entertainment. But how do these everyday devices work? We can see touch screens everywhere. They've become a part of our everyday lives. We barely bat an eye while scrolling through Instagram or retweeting something on Twitter. But how does putting a finger on your phone's screen to perform these tasks actually work? Let's explore that in this video. Now, to begin with, we will look at the structure of a touchscreen display first, and then we will go into the physics of it and understand how does a phone actually recognize where are you touching the screen. It turns out that a touchscreen display is comprised of many layers. At the very top, we have the protective glass, which is chemically toughened. And smartphone glasses are over 5 times stronger than normal glass, and that's why the screen doesn't crack easily when you mistakenly drop it. We have the LCD screen at the bottom that produces the images that you see. And between the LCD screen and the toughened glass are several sheets. One of them, the top sheet, is a sheet containing a grid of hair-thin lines of a conductive metal, and this conductive metal could be indium tin oxide or copper. And I have shown them as colored, but these lines are transparent, and of course there are many of such conductive lines on the top sheet. Below that there is an insulating layer. This is an insulating layer which separates the conductive lines at the top from this sheet that also has hair thin lines of a conductive metal, but in a direction perpendicular to the first one. Let's look at the structure of the top sheet and the bottom sheet more closely now. Each of the rows of the top sheet, they also have a metal plate attached to them, and that is coated with a conductive material like copper or indium tin oxide. And similarly, each of the electrode in the bottom plate also has a metal plate attached to it. And there is a current flowing in the top sheet along these blue wires, these blue electrodes, as a result of which there is some positive charge that is deposited on all of these plates. And when these two sheets are placed on top of the other, they form a grid-like pattern which kind of looks like this. So we have this grid of tiny capacitors. Because there is a positive charge at the top plate, it induces a negative charge at the bottom plate of the capacitor. And with no external disturbance whatsoever, that charge is maintained constant by the phone's battery. Now over here you see around 35 capacitors, but on your phone screen you have around 1500 rows. So you can imagine the number of capacitors that are there on your touchscreen display. Now let's pick any one of these capacitors and look at it more closely. So we have the positive plate at the top and the negative plate at the bottom. Since there is charge on both of these plates, there are electrostatic field lines which go from the positive end to the negative end. And these fields aren't getting disturbed because there is nothing that is disturbing them. The phone's battery is maintaining a constant charge on both of the plates, and the electric field is also maintained with no disturbance whatsoever. But now comes the interesting part. Let's say we bring a conductive material like a finger, something conductive like a finger, close to one of this capacitor. Why don't you pause the video at this point and think about, will the presence of a conductive material like a finger, will it affect the electric field in any way, or will there be no effect? Pause the video and think about it. Alright, hopefully you have given this a thought. Now, human body is made about 60% water, and pure water is an insulator, but the water that is inside of us is impure. It is loaded with ions, atoms or molecules that have a net electric charge. And the presence of these charges changes or distorts the electrostatic field that was present between the capacitors. And now the field lines look like this. It is as if your finger is stealing away some of the electric field lines from the capacitor. Now the electric field strength has decreased slightly, and we know that electric field strength is equal to V by D, the potential difference between the plates divided by the separation between them. So if the electric field strength decreases, even the potential decreases. This drop in potential is detected by the sensor, and then the sensor pinpoints that particular location where the voltage has been dropped. And that is how basically a touchscreen display works. Now there are a couple of things that you might have experienced. Something like if there are water droplets on your touchscreen starts behaving very randomly as if you have touched at multiple locations on the screen. That is because presence of water distorts electric field at many of these capacitors, and the sensor detects all of those changes in the electrostatic field, sends that signal to the processor. So your phone ends up doing multiple things at once, maybe opening multiple apps all together. And on the other hand, if you're wearing gloves, you might have experienced that you aren't able to operate a touch screen. That is because the fabric of the glove is an insulator. So when you bring your finger close to the screen, there is no change in the electrostatic field and there is no voltage drop and nothing is detected by the sensor. Now the touchscreen displays that are used these days, they do not really use this grid-like pattern that you see on the screen because there are a couple of disadvantages which are associated with this. So one of them is that this pattern starts becoming visible because you have two layers on top of each other compared to one transparent layer which might do the job. Now you have another transparent layer beneath that. So the pattern starts becoming visible slightly, and that is not the goal. The goal is to make it completely transparent so that the images that are formed on the LCD are clearly visible. And secondly, the electric field is inconsistent. That is because you have these capacitors and the electric field is strongest in between these plates. And there are these spaces around and between the capacitors where the electric field is not as strong as it would have been between the plates of the capacitor. So when you bring your finger closer to a capacitor, there is not enough distortion of the electrostatic field and there is not enough drop in the voltage for the sensor to detect it. So there needs to be some change to the design of how the grid is formed. And turns out there is one grid that is followed these days. Let me make some space. That pattern is called a diamond pattern. Now over here, the plates are not on top of each other. They are shifted slightly. You can imagine that the top sheet has been shifted slightly to the right and the bottom sheet is where it is. So as a result of which, the plates are not on top of each other, but the plates kind of look like this. And there is an advantage to this because now your electric field lines, which could look like this, your electric field lines are not localized or not concentrated in one particular space. They are more spread out in the space so that when you bring your finger closer to the plates, you get a proper distortion of the electrostatic field, which is then detected by the sensor and the location is registered by the processor. So this is the technology that mostly is followed right now in touchscreen, and the basic principle still remains the same, which is that bringing in a conductive material closer to the capacitor changes the electrostatic field, which then lowers the potential or there is a voltage drop that is detected by the sensor and that particular location is pinpointed and registered.